Welcome to the first DOL seminar in July. It's our pleasure today to welcome Dave Emmitt. And I stole his resume off his website and got his bachelor's degree in physics from East Nazarene College in Massachusetts. I must admit I haven't heard of that, but small school. Went on from there to the University of Virginia, got a master's in environmental sciences and a PhD in meteorology, and retained a connection with University of Virginia for the rest of his life, I guess, in various capacities, where he's now an research associate professor. You give your title, yes. Scholar in residence, okay. Anyway, he's got, there are too many things to list here, but in, let's see, 1983 started with Simpson Associates, I guess, and is now the president and senior scientist of Simpson Weather, and he'll tell you some of their activities. He has a whole page of interactions with NASA, NOAA programs throughout the years, EPA, DOE, a little bit thrown in, and he's also a fellow of the American Meteorological Society. So I think at that, I'll welcome Dave.
All right. The rules were simple. Turn this gadget on and stay over here. So I'll just give you a warning. I have a lot of slides, and I will fly through some of them, but anybody that sees something there of interest can stop me or ask me for the slides afterwards. I'm not going to tell you how many because people get nervous, but I will finish in 50 minutes. I want to give just a brief history of airborne Doppler wind lidars. And I'm going to focus on technologies of the lidars that I use with SURPASS, ONR sponsorship, NASA sponsorship, Army Research Lab. A brief comment about coherent detection versus direct detection. I operate with coherent, but I don't want to leave these guys out because there's some new technologies on the horizon, some of them being developed right here in this town. And then I'm going to focus on how I've used the wind lidar, TODWL, Twin Otter Doppler Wind Lidar. And we'll talk about some complex terrain. This is supposed to be EDMF, eddy diffusivity mass flux. And then the other system that I operate is on a P3 DWL. It's a new laser compared to the Mag-1A. But that was flown in T-Park and typhoons. We flew about 170 hours, and I'll show you some results from that very quickly. And then, what are we doing right now? We'll talk about the NASA Langley version of the coherent detection. And I've just been funded for two big missions in the Arctic. Put together a team. And one member of the team is here from CU, and then Mel Shapiro, and also Ohio State. Because anybody that knows me knows that I know nothing about the Arctic. I mean, I can point it out on the globe. So I had to get some experts there. ADM is the Atmospheric Dynamics mission, which is the European mission that's hopefully going to launch next year, and NASA wants to be part of that CalVal. ADM is a Doppler wind lidar in space, the first one ever that will be put there. It's non-scanning, so it's not giving you the full vector, but I'm participating in that. And then talk briefly about the total system. I'll show you some work we already did where we overfly a C-17 and map out the wing tip vortices. The P3WL is right now getting ready to go on the N42. The season will just hold up till we get it on there. And then T-Wolf for tornado research. That's not airborne, but it uses the total system in a mobile weather radar truck, and working with Howie on trying to get that done for the second time. Sorry, that's where we're going. I put this slide in here because this is the pull. This has funded a lot of the development of airborne Doppler wind lidar up to this point, at least the research versions, and it's the idea that we're going to go to space. So of course you're going to start with an aircraft system. So we had WindSat and LAWS was the big one that I got involved in. Sparkle, I was mission scientist on that. That was to put a wind lidar on the space shuttle just for a 14-day mission. GEM-CDL, I worked with the Japanese on designing that, and was just hiking with a guy the other day, and he says, that's coming back. So maybe we'll see that one come back. And then a couple other. Here's ADM, the one I just spoke of. And there's been several other aborted attempts to get something in space, but right now NASA has in its hands a proposal to put one on space station. And they're considering that now. And Ball Aerospace has the lead on that. We can go back to Ron Sweetso's efforts with a very small airplane, a bistatic system, send out photons this way, capture them with the other receiver. I think his claim to fame was measuring a water spout. And since then, this is where I got involved with the Convair 990. I don't know if you remember CCOPE, all right? And that was side-looking. And then we have the DC8, NASA, NOAA, the MACAWS system. The Germans got involved with the DLR, putting on both a variety of wind lidars on theirs. And then we had this fairly short-term effort here back in the early 2001, non-scanning, looking for turbulence. This whole idea, you could look ahead of an aircraft with a wind lidar, detect turbulence, and get everybody buckled up before you hit it. Or adaptive flying. Then the Twin Otter. This is when I got involved as the PI on this. This was handed to me basically by the NPOS program, and that's a 2-micron system. You hear a lot about that today. The Navy P3, funded by Ron Farrick on the ONR, and did the Typhoon research. Now I'm also working with Dawn, and that's what we're going to fly to the Arctic on the DC8 next spring. And this fall we're flying it on a equivalent of a King Air. Ball Aerospace, different frequency. Some interesting work here on wind lidars in using direct detection. And NASA Goddard has the Twilight system, which is also in the ultraviolet eye safe, ultraviolet molecular, doesn't need aerosols. So the rest of my talk, though, is focusing on, here's another history chart of all the organizations that have been trying to use wind lidar. Here's what I've been working on, and now we can put a square here for the Dawn system. I show you this because this is CCOPE, and this is what got me going, was this is the kind of density of velocities, 333 meters part vectors on a plane, looking sideways out the Convair 990 and later DC8. This is just the XY axis looking back, storm back here, outflow from a storm. And we saw colliding gust fronts and various things. I put it in the potpourri class of missions. Let's go out with this instrument and measure a lot of things. San Gorgonio Pass, where they have wind energy. Cloud top, obstacle flow. This document. So we would do that, but we would never settle down and focus on one issue or one scientific question. And we are now at that stage. But that's what got me started, got me energized, that we could actually make wind measurements in clear air, because otherwise I was always working with radars. And they left me wanting, because I was more interested in nocturnal boundary layers and what was happening outside clouds rather than what was happening in them. All right, so under data utility, we've been using it for severe storm research, flow and complex terrain, organized large eddies, marine boundary layers. I've been doing this a lot for Ron Farrick out of Monterey, Surpass, currently doing a lot of both theoretical and other observational kind of work there. Evaluation of mesoscale models, you'll see that today, hopefully, quite often. I'm often, in fact, I don't know any program I'm in now that I design that doesn't have some version of the WRF model that I am beating my observations against. um, and had a long discussion about that at CU this morning. However, there has been very little of taking the data, ingesting it through the front end, through a DAS, and seeing what its impacts are, except for with a few exceptions. This is with the old MM5 out of the NPS group. And what you're looking at here is this is the model. How you like that Ekman spiral there? Perfect. And then these are the total. These are wind barbs, and in between are the aerosol panels. So you're seeing both. You can see both. In this case, what this is not the aerosol, but an average velocity. So you see two jets. But we often plot the aerosols in it. The only reason I'm showing you this is that that's the density of data compared to the model at this point. And that's the value of these profiles. We are oversampling for the model comparisons. All right. So this is the system that I've been using the most. This is the one that Vonda's familiar with. It was part of Matterhorn. We flew it at the Matterhorn. It is out of Surpass, Navy Post Grad School. It has the DMP, PMS, Old Nolenberg, whatever you want to call these probes, but the particle probes are for various sizes. The scanner, there's only two that I know of, and if you want a system that works and does real good science, better than downward looking or upward looking, this is it. This is the secret to most of what I do, is that scanner. It's not inside. It's being able to point that beam wherever I want, up, down, forward. I can scan it conically, up, down, stare, nadir, whatever. So that is hanging on there on the side. I want you to take a look at this. This is a little cruise missile. It's basically used more as a target, but it's been gutted, everything but the navigation and stability system. And inside here is a little camera and a bunch of flux measuring devices. I'll show you what we're doing with that. That drops down about 1,000 feet below the Twin Otter, and we do that over water. This is another picture, the Twin Otter, the scanner, and I only take 2 of those racks. I've got it down to 2 racks. It uses a lot of space. And then when it's not there, and this is what Howie's anxious to see go again, we mount it right here. Here it is, with a different type of scanner. It's the same innards inside with a K-band phased array antenna, and just pray that Howie doesn't put it in harm's way. But that's what we did one time, and we've had some equipment problems. I hope we resolve those. Oh, this is just a joke. But this is this is the innards. There's our scanner, there's our transceiver, and there's the rack, and there's Kevin. And this is what we do when they kick us off the airplane and we still want to have fun. So we have to give it a name, P-Wolf. Now here it is mounted on the Navy NRL P3 side mounted. Back here it was pre-painted. And there it is in its rack and a quarter or so. And this is the new vintage. This is a smaller system, fewer cables, less weight, but still coherent detection, working in the spectral domain. And this is the one we flew in the Typhoons, and this is the one we're mounting on NOAA's P3. This is what it looks like here. This is built by Lockheed Martin CT locally. This was the first one they ever built. It was built under an SBIR, and that's what we're flying. I'm going to skip through these data products, except that just to say, we measure winds, and we can measure just vertical winds. We can measure horizontal winds through a conical scan, but we also measure backscatter, so we can talk about where the top of the boundary layer is. We can talk about salt sprays. I can sort out rainfall from air because I'm in the spectral domain, so I see the velocity of the rain, the hydrometeors, and I see the velocity of the air as well, and I can see the drag on the air. I can measure those two velocities. I can measure the velocity of the salt spray versus the velocity of the air around it, so I can say whether they're accelerating or not. All of that's in the spectral domain. And I'm using this very much with the C-17 and the Wing Tip Vortices. I'm looking at velocities all in the same range gate, ranging from plus and minus 100 meters a second. They're all in the same range gate. So, but we have some limitations. 50-meter overlapped range gates on this system. The Dawn system, which we'll be flying in the Arctic, is a little less than that, more like 20 meters. But we do a very high rip rate, about half a meter along the flight track. So we're resolving that. And each one of those shots stands on its own. We don't have to integrate it. So each shot provides you with a velocity. The reason you average is to get more sensitivity, but the precision is based upon picking a peak in a spectrum. And as long as that peak is above the it has a good SNR, you'll pick the same peak, no matter what. And if you average 5 together, you're averaging some local variability. Plus, you can increase your signal to noise in weak signal regimes. But that's the advantage of coherent. We make a complete wind profile about every 20 seconds with precisions which finally got past the reviewers of maybe 5 centimeters a second. That's on an airplane. So that's what you get with coherent. But you have to have aerosol. So you talk all about mid and upper tropospheric winds. I like those cirrus decks. I love the cirrus curtains. But if I don't have those, you've got to go to direct detection molecular. So depends on your science. This is great for boundary layer science. That's what I do. I'm going to just skip this and get to the T-Park dropson comparisons. Now, I know you work with dropsons and things that go up, things come down, things that stay down. You have to do these. But I like to compare these, compare these comparisons to the old radar rain gauge comparisons. You know, we used to argue about who's right. You're both right. You have different error bars, but the old ZR relationships, I mean, which one should I be using? All the drop size distrometer stuff. Okay, here I am measuring winds on a moving aircraft, and the loci of my samples is a cycloid. And I'm going to combine that to give you one statement of the full vector wind profile as a function of height every 50 meters to within a few centimeters a second. Well, how does that compare with a dropson that was dropped out of the airplane that came down its slanted route and sampled something differently, even though it's a GPS son and may have less than a meter per second measurement error? What's its representativeness? Would you trust that if you're in a model? Would you rather have that or rather have sort of an average over a kilometer? So here's one where we went into Typhoon Hagapit. We came in from the top across the rain bands. Here's the eye, and we made measurements to within a few tens of kilometers of the eye. I couldn't convince the P3 guys to go any closer. This is another blow up of it. And here are some comparisons. We did dropsons, quite a few. And what you're looking at here is the black line is the dropson. All right? And the 3 colored ones is my sounding before it, during, and after. So that's why there's 3 colors here. That's speed, and this is 0 to 40 meters a second. These are about 25, 30 meters a second. And over here is wind direction. And no fudging, okay? No adding some fudge fact. This is just raw comparisons. Here's some low wind speeds, 5 meters a second. There's your Raywin-Son. And real directional differences, supported by a whole lot of soundings compared to the Raywin-Son. So, all right, so you put the Raywin-Son in, and I work with Sasha Pu. She runs her WRF version of the WRF. We all have a different version of the WRF. And that is a good sign that that particular dropson is not very representative of that particular area. Clouds. Clouds are not as bad as maybe we went into this thinking about it. Again, here's the dropson. There's our winds, about 30, 35 meters a second or so. We got that from this thin cloud, but we kept on going and made winds measurements all the way down here from a mixture. Hey, we're in a typhoon. There's a mixture of all sorts of things going on. I mean, it's a very, very hazy region that we fly in. All of this is below 2,500 meters. All right? And here's another one where we had a elevated aerosol layer, but we were able to make measurements throughout with this system. And this profile here is done in about 20 seconds, 20, 25 seconds. This is a PowerPoint slide, but we published a paper on this. This is hurricane track and intensity. And the black is the best track after the fact, okay, reconstruction, reanalyses. And if we put in the lidar winds, we get the green, and without the lidar winds, we got the red. And that was on track. And intensity, again, this is from the reanalysis or best track, and our control was without the lidar, put in the lidar, and we did better. And we did three of these cases. So this is my point on here. The airborne wind lidar is now beyond the technology demo and the potpourri kind of, let's show what we can do here and let's show what we can do there. And let's see how many people we can get excited and how many advocates we can build up. We did that. And I think we're now where we're getting critical mass observations. That's a lot of observations just focused on typhoons. And you'll see some others that we did at TODWL with the program that Vonda and I are associated with, or were associated with, still associated with. And it's, focused on a question and collecting enough data to make a really critical contribution. So now these are some slides from some presentations. I kept them because they show Ralph Foster from APL University of Washington works closely with me. We have been for over a decade now on organized large eddies and low-level jets over the water. Kevin Godwin, he's actually a student, got his degree at UVA. He's running his own little LLC. And then Steve Greco and myself from Simpson Weather. But organized large eddies is something that we've been studying now for quite a few years, mainly over the water, but also over the Salinas Valley and other places we've been. Organized large eddies are ubiquitous, even if there are no cloud streaks to tell you they're there. They're aerosol streaks. And so we're trying to understand their importance. They're there, and the question is, are they important in the flux? The EDMF, eddy diffusivity mass flux, that MF, is usually meant to cover convective fluxes beneath clouds. But these guys are shear driven. They happen in stable boundary layers. And they're there a lot. And that's why we're going to the Arctic to study how these function up there at the ice water edge. We know they're there, trying to understand more about them. Again, this just remind you of what we're getting for resolution with the system we're flying, 50-meter line of sight, less than 10 centimeters per second on all three components. Maximum range depends on the day, how much aerosol. Too much aerosol, we get too much attenuation, extinction. So we play a little dance with that. 20 seconds is the minimum. Most of the time that's 25 seconds to get around. Our sampling frequency depends on which system. We're trying to run a 500, I'm sorry, this is 100 hertz, that's the PRF, but we're running 500 hertz now. And then we digitize a signal at about 200 megahertz for the numbers people in the room. So when we're trying to understand these organized structures in the boundary layer, besides low-level jets, that's when we drop this towed platform down here below the Twin Otter. And this is just showing you at the Twin Otter level, we're measuring fluxes. We have the whole flux system on board. In between I'm painting by, not this, but I'm looking ahead at about 60 degrees below the horizon. And I just sit there and I prospect. The aspect ratio on this is not right. And I know you can't see, but if you see right here, these little channels, we're trying to write a paper about them now. Mel Shapiro's guaranteed me these are brand new. No one's ever known about them. I don't think that's quite true, but no one's seen them like this. This is turbulence. We're measuring turbulence directly by the spectral width of our return. This is SNR. You see this layering of clean, and there's not a cloud in the sky. So this is all aerosol layering. And this is the line of sight velocity, and you can see structures in here too. Those are some rolls. So what we're doing is measuring fluxes here, mapping out what the intervening boundary layer looks like, what structures are in there, and then we have the towed platform coming along here, skimming the waves, actually trying to skim the swell, not the wind waves, and trying to stay the same height above the water. All right, so we're not getting into, 10 meters and then 7 meters and then 10 meters. And then we do the fluxes below. And that's what we're putting together right now, that story of just how, when you have these structures in the atmosphere, how does it change these fluxes and these fluxes? So this is that prospecting I talk about. This is not getting wind profiles, but we get about 2-meter vertical resolution by doing this, and about 50-meter horizontal resolution, because now that 50-meter resolution is in the horizontal. But we do 10-meter sliding range gates, which, with some trickery, we're actually resolving some features down to about 20 meters. Here's another example, a blow-up of these vertical features terminating up here on this aerosol. But this is turbulence, direct turbulence. It's nothing else. And it stays non-diffusive. In other words, this is 50 meters down here, and it's 50 meters up here. Actually, I'm resolving it to 20. So that's the intriguing thing from that study. There's some more. The reason the ocean surface looks like it's moving up is that the aircraft was slowly was getting out of our range. So, but anyway, you can see those features there. And at the end of all this, we love to see skewness because that tells us there's more going up than down. So there's a net something. That's what if it were 0, it just means, okay, these things are rolling around. They're not contributing much, but we're seeing some net transport. So the combination of an airborne wind lidar and that controlled towed platform, I think it promises a transformation of how we investigate air-sea interaction. That's a unique capability, and we're tackling some old problems with new technology. So let's get to mountain waves and energy harvesting. These are combined because I've been funded by both DARPA and now the Army to work on using natural energy in the energy in the atmosphere to extend flight of UAVs, and using lidar and any other technique I can employ. We're using the WRF model here, and this is the one that NCAR is running for Dugway in this case, I think. Or I may have this mixed up with the one that Zasha runs for Ruby Mountain, which was on our way to Dugway. Regardless, we run it down to 333. I think NCAR stops about 1 kilometer. But we run it down to 333 meters. I'm not real comfortable with 333 on the grid points, but then we invoke the LES for the smaller scales. However, Ruby Mountain was on the way. This was 2012, flying from California to Utah to participate in the Matterhorn, which was mountain meteorology. And Ruby Mountain is sitting here. Here are the salt flats, Great Salt Lake. And we flew coming in this way, and I sensed something was kind of interesting, like the plane going up and down. So I said, could we do this again? And the pilot said, yeah, we're carrying too much fuel anyway. So we went back over it twice. And these are not things you put in the flight plan. This is the topography and exaggeration. But that's where we flew over those features. This is the WRF model putting out waves. All right, and they're slowly increasing in wavelength and decreasing in amplitude, so they're being damped. We came right through here. The second time through, I'm pointed straight down. I'm measuring just vertical motion, the best I can. This one right here, it's at level 27. It's actually about 4,000 meters. Okay, it's right at our flight level. Just above our flight level. This is a blow up on it with the horizontal winds because I wanted to see how they were reacting. So you have these, it's just a blow up of what I showed you before. Again, we're coming right through here. And so the question is, that's what the model said we should see, so what did we see? This is the flight path. Came here. Can we turn around? Yes. Came back, and then went all the way through. And I'm only going to show you one of these, but here's what we see looking down. We do have a problem in the boundary layer with these systems because over water we get very little return off the water, and therefore we see almost to the surface looking down. Over land we're running full signal without any attenuation, and that was my fault. I should have attenuated it, and it blinds us for about 250 meters. That we're actually processing now down into about here. But in this display, but here's what you see. This is a big -6 to +6 is the, so right in here you're seeing over 6 meters per second up, and right here you're seeing more than 6 meters per second down, but these are more where you'd expect rotors. Down here hugging the ground. And the wavelength doesn't fit the model at all. These are all inside the resolution of that model. The model is resolving this broad area of up and this broad area down, and then down again. So as neat and tidy as that model is, you don't quite see it that way as you fly over it. So what? I mean, what do you expect? But that's just one snapshot of looking at the mountain wave as a target with a vertical velocity measurement. From the west to east. From west to east. And yes, this is in the east. This is the flow is this way. And it was very strong. That's why we had so much fuel on board, and they didn't mind going back and rerunning it because of they didn't want to land with too much excess fuel. Landing heavy is not a good idea. So anyway, there's a whole presentation on that. I don't want to get into that, but I think what we're showing is clearly, we have a capability here in the vertical mode to validate some of these model predictions of waves. I have an interest in it because I want to find out what they look like when I look at a wave like this with a UAV versus looking at it like this, and for a variety of other reasons the military is paying me to look at it. All right, now complex terrain. Stefan de Vecker is also at the University of Virginia, and he's been working on this with the Matterhorn, mountain meteorology, and myself and Steve and Kevin again. Here we have Granite Mountain on Dugway Proving Ground, salt flats on this side, a little bit of brush and sagebrush on that side. And each one of these dots is a complete wind profile. So we come in and we just go back and forth over Granite Mountain. I was interested in, what I do, my normal scan is a 12-point step stair, okay? And then at the end of that 12-point step stair, I point the beam straight down, corrected for nadir, for pitch, and stare for 5 seconds. So the idea was, can I tell anything about the vertical velocity from the stair And anybody that's processed radar data knows that you have a DC offset when you do a sine wave, and you can suggest that part of that is vertical velocity. So how does that vertical velocity estimate compare to the stair, which is looking just down in a mountainous terrain? The other thing was, here's that cycloidal pattern I was talking about. There's number 1. Well, I was actually coming this way. And I wanted to know, here I am combining data from that spot with that spot. And now I have a funding to develop a totally new way of putting these data together so they make more sense in complex terrain. But I stare, if you build it up, this one's at 1660 meters. That one's at 1484. This is at 1385. And I'm combining those to make a wind profile? I'm not. But I just wanted to show that, and Stefan Devecker and I are working on and we got a graduate student working on a process that I propose. We'll see if it works to do a better job of combining these different lines of sight. Again, here's flying over Granite Mountain, producing speed. This is from the lidar total system. Speed, direction, W, and this is the intensity of the signal. So you can see we're hitting the ground right in here. And the winds, of course, are going to 0, just below that point. W nadir is a function of roll and pitch. Again, this is 0.2 meters a second, 0.2, 20 centimeters a second. That's the sort of numbers we're getting. They're down in that 10 meter per second over mountainous terrain, which is anything but homogeneous. This is a map of the vertical lines of sight. Can you make sense out of that? If you can, come up to me afterwards here, because I'm struggling to make sense out of it. But those are those 5-second stairs. And to put them all together when you in a complex terrain is probably totally foolhardy, but I took the data, and I'm kind of curious if it has a message in there. I haven't probed it. Okay, WRF model at these 5 points. Upwind, wind's blowing this way. Just downwind of Granite Mountain and further downwind. How does the WRF model compare to our wind profiles? And they're within, I believe, we tried to get them within 10 minutes of each other. I mean, we tried to pick a time where we were flying. The model isn't run every 10 minutes, but we were flying there. All right? So, quickly, model, wind speed, west, upwind. Here's the model. It says we should see that. Here are the 5 locations that I showed you with pins. And here are the 5 soundings with total. There may be some modelers, and I don't think they're in this room, that would say, that's pretty good. They're all less than 10 meters a second. I mean, certainly, if you're looking at, I do precision airdrop work for the Air Force. I mean, you'll drop your package, your pallet, in a much different spot if you use that to calculate the release point than whether you use that. Here's wind direction. The models don't do well with strong shear, at least the ones that I've used. They just don't always get these shears right. It's suggestive, but this is what we found. And then just east, you have, again, this is the model's 5 values all in a line, and that's the total soundings. You don't ever expect 1-to-1, but you'd like to see the jets in the right place. You'd like to see the inflection points in the right place. You can't expect 1-to-1. They're not going to ever be that. In fact, I'm working on a project now where I'm doing everything in phase. I mean, I go through and map things with the wind lidar, and then I have my model, and then I try to phase shift it in time and space till I get the best matchup. Because that's the only way you can really. Do they capture the essence? These scores don't look good, and these are not interesting. These are very unsatisfying to the military, because they've got to make decisions on this is terrible to them, I mean, they'd like to have this, but how do you get this? They get this like that, and it looks good. There are no arrows that go the wrong way. There's no noise. Models look great, but they know that they aren't going to drop it in the right place. On this was less than 1 hour. It's almost analysis, but it's, yeah. Yeah, we picked a good time from the model and then went and searched our database for when we were near there, because we weren't. This is the NCAR version. We have run the other version. We've run our own version, and Zasha Poo's run hers down to 333. Like I said, you're only going to come up with different disparity. You're not going to improve. All right, and then if you go further east downwind, further away from the ridge, we get into this interesting place here where you got a lot of wind direction shear, and total suggests that you might have a little bit of it, but not as much as the model suggested. So. All right, so the summary from all this is that the total system functioned extremely well. We had no unscheduled downtime. We were in a place where we have a lot of other data, and this is being worked on by graduate students, particularly at UVA, but I think there's some other. I just got a paper to review by another group. And we're really trying to work this validation, work together with a model. We go out there and take a few data points. The model's running all the time. So you really want to see how we can feed back into the model more than we're doing right now. Right now, we're just simply saying, we don't agree. We don't agree. It's not very satisfying. We want to find out what is it that we're collecting. And that's what I was meeting with CU folks today. What are we collecting? How can it be folded back into the model? Only through parameterization or just flagging. One of the best things you can give to a user of a model is your error bar. Don't trust it here. I mean, it's got an answer, it's plausible, it's physically realistic, but don't trust it. And if we could even do that. Okay. So, 2 more short stories here. This is some work I just did in April, actually, of this year. This was done at Yuma. It's in support of C-17 airdrops up to 4 tons. It's amazing what they drop out of these things. But the whole idea is to program to put them in tighter. They call it the echelon. So the first guy in is C-17 generating these big wing tip vortices with 100 meter per second ups and maybe 80 meter per second down. And that's how they get generated. And they persist with velocities like that for maybe a minute or 2 under some conditions. But they picked the very worst conditions that they ever found by throwing mannequins out the airplanes and watching them go up and down, that they use 5 minutes. So they have this program on a flight spacing FSR reduction program. And they've asked me to work with them on it so that there are days where convection destroys these things. There are days where shear destroys them. And situations that destroy them that are either day or night. So they can maybe get down to 2 minutes rather than this safety. 5 minutes is like the worst they've ever had. So that's the nature of the program. So these wing tip vortices are, you can go on Google and find a bunch of them, but these are the guys that usually they're looked at airports. But here we're talking about things that are happening 550, 1,200 feet above the ground. That's the C-17. I show that. If you saw the picture of the twin Otter, we look tiny. But this guy, even with these winglets, is generating very large wingtip vortices. Something like that schematically, and counter-rotating. Again, in this region here, you've got 80 to 100 meter per second winds. Actually, not right there. They're really close to the center. The actual strongest tangential winds are right near the center, about 2 to 3 feet from the center of the vortex, and then they trail off. So this was a schematic of the Twin Otter sitting up here. I have a blind range of 400 meters right outside my window, no problem. Here's a C-17 scaled, and I am doing this with my side scanner. I'm sitting on the side, but I can look back underneath Twin Otter. So I'm just doing this as I fly along. The key point is lining up right over top the C-17. I have my own GPS, the magic of GPS. Everybody's GPS is get you in the right spot at the right time. Here is our going back and forth, and that's the C-17 flight track. And this is about a minute after the C-17 was there. In other words, actually the C-17, yes, did this, and we came this way. So we're counter-flying where the C-17 laid down its vortices. We come back over top and see what they look like back to about 4 minutes into their, after they're generated. That's what one looks like in one of our presentations, which is up, down, up. Not too exciting. We don't have the greatest resolution. But this is taking one of these sweeps. That's the C-17 track. This is the SNR. You can see where we hit the C-17 in this case. We did that a number of times where we'd actually go right over the C-17 purposefully to get that index. And the line of sight is where it belongs to. So our navigation using the GPS, I would say, is within about 10 feet. So we're all done. So I was pretty pleased with that. I just show you this because this is the world I live in, spectral domain. If you're into direct detection, you don't work here. You're into photon counting and that sort of thing, intensities. But this is outside the vortex, very simple spectral feature. And of course, this is getting two contributions. You get these tortured spectral features showing you that there's a lot going inside your sample volume. That's just one volume, and you have to make sense out of that. That's what we've been doing now. One of the metrics, of course, is the sync rate of the, so if you follow them long enough, and we have a model, we're working with Draper Labs on this, and you get a sync rate of about 1.5 meters a second. Once they're generated, then they start to sync. Sometimes they go back up, and sometimes they bounce off the ground. But most of the time they sync. Again, bring in the model. So again, this is the NCAR model. NCAR runs their model for a lot of the military facilities. This is for Yuma. So they ran the one for Dugway. They're running this one for Yuma. Here is the wind speed from the model, and this is what we actually got from Raywensons. All right, in fairly close time, but not perfect. And this is wind direction. This is daytime. And thermally, we're not going to argue with them much. We have, at least from the soundings, there's all these problems right near the surface, suggesting a super adiabatic, which you'd expect on a hot day in Yuma. But what I was most interested in was night, because the Army says we own the night. So I said we got to do some night flights. So now the model and the observations start to deviate in different ways. The model again being the dashed line, not showing this wind direction shear at all, and certainly not showing the depth of the boundary layer, the mixed stable layer, I should say, compared to the model. And that's what's critical. This is the most critical thing right here, because they're dropping right here at 550 AGL. So just an example of what we're doing, and we're now funded to examine all this data, get it back into the Draper model. But what's happening is we're actually generating a whole new concept at Simpson Weather as to how to deal with these things. Because they're not always nice rolled up vortices. They link, they burst. I don't know how many of you used to play with smoke rings, but I used to do that. And it was just fun watching these things go through their life cycle. The same thing here. They're not immune to shear, they're not immune to convective turbulence and so forth. All right, Dawn is our last thing here. This is most recent. Dawn is a system developed at NASA Langley. It's a coherent 2-micron system. It's the most powerful 2-micron system in the world by far. It was built for a space station, and it hasn't gone on space station, but it's built as the engineering unit. So this broke all the barriers as to how many joules you could get, and basically watts out of a coherent system to date for wind. It looks like this. It's not all that big, but this is when it went on the DC8, flew on grip. But again, it's just these wedge scanners, only looking down with a refractive index and a wedge-shaped scanner. So they're just rotating and changing where the beam goes. This is what we're doing, and that's what we're going to fly next May, June in the Arctic. Right now, we're not quite sure. Could be Thule out of Greenland. We're working with ESA and the DLR in Europe, coordinating that. But right now, the first one is on this aircraft right here, and this is going off this October, November out of Kangerlussuaq and off of Greenland, and we're going at a crazy time of year, but the main purpose is to make sure this instrument works and is ready for the ADM CalVal, and to do some polar science as well. If you're getting the picture that these systems, that these capable systems are big, yes. They take up space. In fact, when you get all done with the survival gear for Arctic cold survival, only I can fly on here. Right? So I have to operate it and do the science too. And I'm training one other person that's flown lidars before. There's no room for a second observer. Unless we go single pilot and over the water and whatever. So this is really just to test ideas. The DC8 is dedicated to this lidar in May and June of next year, and so that is a much more ambitious program. So this is the last slide. The total is now going to be used in the second series of these Wing Tip Vortices flights, but we're going to do it near Monterey or Seattle. The Dawn is to be flown on that UC-12B to Greenland. Polar Winds is the project that I'm PI on, and this is a headquarters request that we do some ADM CalVal preparatory work. Dawn to be flown on the DC8 next spring. The P3DWL is on the NOAA's 42, and T-Wolf to be deployed with the K-band Surpass mobile weather radar. So if we can keep all this hardware running, we'll be focusing on real science issues, and in every one of these, maybe I don't know about this one. We'll be running these with models, going at the same time. That's what CU's generating for us right now, are test model runs of the polar WRF and the coupled WRF, coupled with the surface, with the water, something similar to COAMs. So we're running those models, and we're using those to guide our sampling strategies. Long legs, short legs, revisit times, all that. All right, thank you.
Thanks, Dave. Questions?
Do you have enough aerosol up in the Arctic to get
Yeah,
a signal?
well, we were funded for light, glass, and Calypso to study those systems. Those were all laser systems, aerosol detection systems, to find out what our cloud porosities were for a laser in space. This is all being funded by the ambition of putting a wind lidar in space, and aerosols. And so a member of our team is Dave Winker, who was PI on Calypso, which is still up there flying. And, you know, we've been watching that carefully. Yes, the answer is yes. Clouds are our issue. We have aerosols, because we're working the boundary layer. It's the clouds that I'm trying to figure out, if they come in for a day, do they stay for a week? Because I only have 2 weeks. So I have to have some contingency plans. And But there are aerosols, and when the winds are blowing, there's plenty of ice in the air. We only need one ice crystal per cubic meter to get enough backscatter to make a good wind measurement. So it doesn't have to be thick. You can look up on a day where you don't even see subvisual cirrus day, and I'm happy. I've got tremendous signal from that far away. Those ice crystals are great. But if you give me a cloudless, cirrus-free day, I'm going to probably end about the top of the boundary layer.
You emphasized multiple times comparison with models. And so it's aside from showing profiles at the time of observations, pulling things out of model, have you developed any other techniques of comparison? Because that is a really a difficult thing to do, what you've been showing here. Mm-hmm. The timing in the model might not be just right. It all depends on the input, phasing. Boundary and initial conditions, and so you might just not get the right timing. So what have you resorted to in these type of comparisons?
Oh, the local pub. You get frustrated trying to make these comparisons. But what we do find, what we've been doing is going to the model and asking, what's your temporal variability? What's your spatial variability? All right, so we start getting into the statistics of neighboring points. It gets us away from a point-to-point comparison. So we've been doing that, a lot of that. And again, you have to make sure you're filtering your data to meet what the model's filter. The model may be 333 meter grids, but that isn't what its Nyquist isn't 666. I mean, there's variability that it's been filtered. So it's very difficult even at that stage to compare. What you're looking for is there a correlation between where it says there are waves and you found waves. In other words, the conditions were ripe for waves, the model said there should be waves, and you found waves. You do the point-to-point comparison, you start raising all these interesting but frustrating questions. But you're right. But looking for variability, we get a little more comfort, yes. Or looking for the presence of for instance, we run the model and say, is this a day that would be good for gliders? There are products out there that do this too, but is this a good convective day with thermals? And then we find thermals. What we tried to do is, what's the density of thermals? And then we got frustrated again. But don't mistake me for doing this extremely thoroughly. I mean, we kind of look at it with our data, because all we have are these snapshots. Some of this is serendipity, some of it's focused. The part we did over in Dugway was very focused. A lot of comparisons. So we're trying to understand what a valid comparison is. Does that make sense? Valid? When can you say the model could do better? Yeah.
I can't resist. For an observational comparison, you must have done CTV versus your winds looking at the same air mass exactly at the same time.
The what?
The towed vehicle, CTV.
Yeah.
From the twin.
Yeah, they fly right underneath.
Right. So,
Oh, yeah.
so is that observational comparison good?
Yeah, that's trivial. Yes. I mean, you're comparing now three systems. Well, the lidar is not telling you anything at that point unless you look straight ahead. All right. But you've got the aircraft system telling you what the winds are at that altitude, and you have that. When you lower it down at different levels, it finally comes into the field of view of the lidar, but you still have its point measurement compared to your cycloid. All right. So what we do is we take that measurement and we do a forward model and say, okay, you took a measurement within 5 feet of me, a line of sight. I take a forward model and say, what should have I seen? And now I can compare that. We do that all. That's what we do with the model. We're flying along. We take all our roll, pitch, yaw into account and say, I'm pointed here. Model, tell me what I should have seen. In fact, that's all automated now. And so we have a scoreboard that says, how well are we comparing to the question of, is this a 1 hour forecast? That's what we're looking at. That's what we have. We're not running a new wharf on board yet. We talk about it, but how are we going to do that? So you could upload the latest, but we're just taking that and saying, That's what I should see out here. This is the forecast for this hour. Now I'm out here. What am I seeing? That's called ADLATS. It's a program that we wrote. But yes, you know, this idea of comparing, you guys are faced with it all the time. You got towers, Raywensons, microwave sounders. Who's right? Who's wrong? How do they agree? How do they differ? And we're faced with the same thing. We're the new guy on the block. You don't see many wind lidars. But I'm just saying the fundamental properties of what we do is along a line of sight. We're measuring extreme precision. We just don't get that crosswind comparison at the same time. We have to look from different directions.
Someone else?
I was wondering if you'd care to speculate on when commercial aircraft will use lidars to look for clear air turbulence ahead.
Well, Boeing came around, and I think Goddard Space Flight Center actually did a study for them, because Boeing was entertaining the idea of having a port in all their new aircraft to accommodate a look-ahead wind lidar. But all the CAT studies, clear air turbulence studies, which were done back by Acclaim, and I mentioned that briefly, brought up this issue. And I don't know, maybe NCAR's thinking of getting a wind lidar put on an airplane. That's another topic. I'll talk about it, because I'm not sure you want to go this route. So if you want to talk about that, we can. But if you're talking about how far ahead you can see at flight levels of what, 35,000 feet? You're not going to use this. There's no aerosol. You've got to use one of those other technologies, that direct technology, and that is nowhere near. There's not a single system other than what the Germans are flying as a model for ADM on an airplane. They're trying to put one on the Global Hawk last month. Okay, that will be the first one to me of any consequence. But Bruce hasn't told me whether it succeeded or not. Ball Aerospace has a rather advanced idea that I model, so I understand it intimately. I had to model its whole performance. But it's interesting in its direct detection. So if you're thinking about putting an instrument on one of your own airplanes, that's another conversation because of what you're asking. How well can you do the clear air turbulence look ahead? And you're not going to use an aerosol system. Now, there's another company out there that has an idea, and I don't know why they're taking so long to, and I can't tell you what it is exactly, but it's Raytheon, and I know what it is. And it takes the best of this and makes it better. And it could work where there are no aerosols. So, very interesting. I mean, there's a lot of development going on. The problem is right now what's driving the development of affordable technology is wind energy. And so you've got companies popping up all over the place with fiber lasers. And I'm going to fly one of them because it's so small. It's smaller than my backpack. It sees out 4K. That may be enough for boundary layer work, particularly if I'm looking down from 3K. So things are developing quickly in the fiber laser area. You've got Leosphere and Halo, and you've got Mitsubishi in Japan. You've got a number of groups here in the U.S. that take bits and pieces from these other guys and put them together and and market it as something else, but it's still the same core systems. But they're fiber lasers. FiberTech will build you one. But these are aerosol systems.
I think it's about time. Okay. You'll be around for another
Oh yeah,
few minutes if you
I'm
want to
not
direct
going
people.
anywhere.
So thanks a lot, everyone.